Today we're going to be exploring the science behind electrochemistry. Essentially, all this demo really is setting up an electrolytic cell and allowing electrolysis to take place. But what exactly is electrolysis, and how does it work? Electrolysis is the transferring of electrons through a substance to effect a chemical change. The transferring of electrons is done by setting up an electrochemical cell. The electrochemical cell contains a reaction called a redox reaction. A redox reaction is where one half reaction loses electrons and one half reaction gains electrons. However, there are two types of electrochemical cells, galvanic or voltaic, and electrolytic. Let's see how these two cells are set up and what makes them different. Both cells include two electrodes, one anode and one cathode, that are connected by a wire. The anode is where the oxidation reaction occurs, or electrons are lost, and the cathode is where the reduction reaction occurs, or where electrons are gained. In a galvanic cell, the electrodes are placed in two different electrolyte solutions and are connected by a salt bridge. The transferring of electrons through the wire then occurs spontaneously from the negative anode to the positive cathode. At the cathode, the positive ions in the solution are then attracted to the electrons and a solid begins to form. At the anode, the solid loses electrons and breaks off to become a part of the electrolyte solution. In a voltaic cell, the system does work on its surroundings. On the other hand, in an electrolytic cell, both the anode and cathode are placed in the same electrolyte solution, containing both positive and negative ions. The power or voltage of the cell comes from a power supply such as a battery. However, in an electrolytic cell, the anode and cathode switch identities, and the anode is now positive and the cathode is negative. The cathode continuously supplies electrons to the anode. Now let's take a look at the components of the electrolytic cell in this demo. Both the anode and cathode are iron nails connected by alligator clips to the battery, which serves as the power source of the cell. The electrolyte solution is made up of a mixture of 3 packs of gelatin, 10 milliliters of 0.100 molar potassium ferricyanide solution, and 10 drops of phenolphthalein. Potassium ferricyanide is an orangey crystalline solid. When mixed with water, it creates a yellowy-green solution that, when heated or mixed with acids, creates toxic hydrogen cyanide fumes. It is also irritating to skin. Here is what my complete electrolytic cell looks like. Now let's see the cell in action. Before we begin, I would like to note that these videos are not of my first trials, as the more I kept practicing, the better my results were. Now let's watch. As soon as the nails are placed in the solution, they instantly start reacting. Notice the different colors forming at both nails. Here's a faster version of a different trial. Also note the bubbles forming around the pink color. Now let's figure out what's actually going on here. First, let's look at the oxidation numbers of the two half reactions. One reaction is as follows: 2H2O plus 2 electrons yields hydrogen gas and 2 OH-. In a molecule, oxygen has a -2 oxidation number, so in order to get a neutral molecule, hydrogen must be +1. The same oxidation numbers apply for hydroxide, as there is only one hydrogen, giving the molecule a negative charge. However, a lone element always has an oxidation number of 0. Since hydrogen went from a +1 oxidation number to 0, we know that water is reduced, so this reaction is happening at the cathode. The second half reaction is Fe solid yields Fe plus 2 aqueous plus 2 electrons. Again, lone elements have an oxidation number of 0, and ions have an oxidation number equal to their charge, meaning Fe plus 2 has an oxidation number of plus 2, and iron has an oxidation number of 0. Now we know that iron is oxidized as the oxidation number increased, so this reaction is happening at the anode. Now let's take a look at each electrode specifically. At the cathode, electrons from the iron nail cause the reduction of water like we saw earlier. 2 H2O plus 2 electrons yields hydrogen gas plus 2 OH minus. The phenolphthalein in the electrolyte solution then reacts with the OH minus to form the pink color. At the anode, oxidation of the other nail then produces electrons which enter the circuit. The Fe plus 2 then reacts with the potassium ferrocyanide to produce the blue complex. This blue complex is also called Turnbull's blue. Now that we know what's going on, let's take another look. If you look closely at the cathode where the pink color is forming, you can see the formation of hydrogen gas and hydroxide. Lastly, the nail of the cathode can never rust or form a solid like we see in a galvanic cell. But why is this? In an electrolytic cell, the cathode is continuously supplying electrons to the anode, hence no iron oxide could form on the nail. This property is called cathodic protection. Thank you for watching this demo today and exploring the characteristics of an electrolytic cell with me. I hope you enjoyed taking a small look into the world of electrochemistry.